Hello everyone, my name is Chen Song, and today I will present our work, Technology-Aware 3D Placement with IoT-based regional planning for soft modules. Here is the outline of my talk. Let's start with the introduction. 3DIC enables integration beyond the traditional scaling limit. By stacking multiple dies vertically, it shortens interconnection and improves the integration density. However, 3D integration also introduces several challenges. For example, thermal hotspot may occur due to limited heat dissipation, and interconnection complexity becomes higher. In addition, heterogeneous integration further complicates 3D placement, since we need to consider constraints such as analog-digital isolation, voltage domain partitioning, and posterior node planning. To solve above issues, 3D placement requires controlled spatial grouping of instance clusters. For example, thermal-sensitive module should be placed in the cooler region. Terminal-related module may require posterior alignment, and different performance or power domains often need spatial separation. The example here illustrates how different modules types may be distributed across the bottom and top tiers. Traditional fence regions are predefined during floor planning. Their size, shape, location remain fixed throughout the placement. This lack of flexibility prevents the placement engine from adapting to dynamic constraints and developing wireless conditions, which may degrade overall solution quality. We introduce a hierarchy constraint that preserves structural grouping while allowing flexible region geometry. Instead of predefined fixed fence region, we group designate instance into submodules. The region's shape, size, and location are determined dynamically during the placement and jointly optimized with macro and cell placement. This maintains hierarchy without restricting flexibility. Now goes to problem formulation. Here we define the problem. We are given a mid-sized design with two-tier and heterogeneous technologies. The input netlist contains standard cells and modules. In addition, hierarchy constraints define group instance set, which we choose as soft module during placement. Our objective is to minimize the total score under the placement, utilization, terminal, and hierarchy constraints. Here we define hierarchy constraint. A soft module groups designated instances together. All group instances must be placed on the same tier and must stay inside the module region. At the same time, free instances are not allowed to enter the module regions. Each submodule can be assigned to either tier, and its region geometry can be rectangular or L-shaped to ensure the compatibility with other EDA tools. Now goes to methodology. This slide shows the overview of our methodology. After passing all the input data, we first perform tier assignment for all instances. Then we solve the placement problem sequentially for each tier. When all the instance locations are fixed, we apply terminal assignment to place the terminal and finalize the placement. For tier assignment, we use K-Hyper for hypergraph partition, constructing submodules as a supernodes. However, K-Hyper is not technology aware. When instances are moved from the one tier to another, their physical area should be evaluated under the target's tier technology. Ignore this can lead to partition that appear balanced, but they are actually imbalanced in the physical area. Therefore, we apply interactive refinement to achieve technology-aware balancing. This slide compares our placement flow with two baselines. Baseline 1 performs mid-size placement and legalization sequentially, but completes the ignores hierarchy constraint. Baseline 2 predefines the region shape before placement, which means the regions are fixed and cannot be changed during optimization. In our flow, we first perform a mid-size placement, where each submodule is treated as a large macro and spread with other objects. After that, we decluster the submodule into group instance and perform a second mid-size global placement, allowing the instance to spread more freely. During the process, IoT-based regional planning is integrated into the flow, so the regions are optimized together with the placement. And here is the animation of the proposed placement flow, including first round global placement, the cluster, second round global placement, and IOP-based region planning. This slide explains the terminal assignment for first-tier net. For each net, we first compute an optimal region for each terminal. When we divide the placement area into a local bin grid. Finally, we use the bipattern matrix to assign terminal to the grids, prioritizing the placement with their optimal region to try and avoid wireless overhead while maintain the legality. Now goes to IOP-based region planning for submodule. In the preprocessing stage, we perform the 3 steps. First, we obtain the result from the second round global placement and divide the group instance to a grid-based map. Second, we convert the placement distribution into a grid representation. Grids with utilization above 50% will overlap with the macros are marked as 1, and the others are 0. Finally, we reserve some boundary select to ensure that optimization remains feasible. Our goal is to select a set of grid and then convert to a region that covers all group instances while minimizing propagation to the global placement. The region shape is constrained to be the rectangular wall L shape. This slide shows the IOP variables defined for each grid. X indicates the input grid, which is generated during the preprocessing stage. Y indicates for the output grid, which is determined by the solver. We also define a difference indicator D, which is the exclusive O between X and Y. For the shape-related indicator, we examine 2 times 2 local patterns to detect the illegal and concave and convex cases, while leaving the remaining patterns are unconstrained. This slide shows our shape constraint modeling. We first fix the boundary grids to 0 to preserve the module area. Then we use the 2 times 2 local encoding to detect illegal, concave, and convex patterns. By restricting the number of these patterns, we ensure the region is either rectangular or L-shaped. For example, an L-shaped region contains 1 concave pattern and 5 convex patterns. This slide shows the macro placement formulation. Each macro location is represented by decision variable and grid assignment variables. We enforce that each macro is assigned to exactly 1 location within a submodule. Macro overlaps are avoided using Big M formulation that encodes the 4 relative positions between macro pairs. These slides explain how we couple macro placement with grid selection. If MKIJ equals 1, it means macro K is placed at grid IJ. Then its lower left corner is fixed at IJ. We also ensure it does not exceed the boundary. Most importantly, once the macro is placed, all the grids covered by this macro must be selected. For example here, if macro 0 placed at 3, 3, with the width is 8 and height is 6, then the total number of selected grid must be 48. An intuitive way to model the region area is to directly sum all the selected Y grid. While it is accurate, but it introduces a large solution space and increases the solving time. Instead, we approximate the region area using the horizontal and vertical ranges. Those expressions are lineable and significantly reduce the complexity. This slide shows the objective function for region planning. Our goal is to maximize the area utilization while preserving the placement distribution. The objective includes 3 cost terms: cell distribution and macro displacement and region compactness. These terms are weighted by alpha, beta, and gamma. Now goes to experimental results. For evaluation, we use the 2023 ICCAD contest at Problem B 3D placement with Blanco. The benchmark includes 7 test cases with up to 740,000 cells, 34 macros and 3 submodules. For preprocessing, we use K-hyper for K-way partitioning. Select some partitions to form the submodules, and hierarchy constraints are applied to those groups. And compared to the naive approach, which is baseline 2, achieve a 21% cost down and 26% runtime reduction. Compared to baseline Placer, which is baseline 1, without region constraints, we incur only 5% cost penalty. And this is the result from naive approach in Cas4H. It is obvious that predefined submodule suffers from several overlap and hard to spread out during the global placement. After the legalization, caused a huge displacement for standard cells and decreased the solution quality. This is the result from proposed approach in Cas4H. Since proposed the second round mid-size placement decast the soft modules, that makes the location of group instance flexible and can be optimized. After soft module regenerate, the displacement for free instances are small, preserve the solution from the global placement. Now goes to the conclusion. To conclude, we propose a multi-stage framework for hierarchy 3D placement with an IOP region planning formulation for submodules. Experimentally, we achieved a 21% cost reduction over naive modeling, with only 5% cost penalty compared to a baseline Placer. Thank you.
All right, thank you very much. We've got time for a couple of questions. And I think we have microphones back there. Okay, another question, all right. So when you use K-hyper, you're trying to minimize the number of connections between layers. Do you have any sort of distribution of where the interlayer connectivity, how balanced is it, is I guess my question.
You mean how to shorten the interconnection between tiers?
Right, and are the connections between tiers sort of uniformly distributed across the core, or are there areas where you might have more dense interconnections than other areas? It's basically a TSV question of where can you make connections, and is it going to be, how do you balance them across the two tiers?
I have a slide to explain how I balance the partition between tiers, because due to the technology difference, the area might be different. So we use the iteratively partition to make sure the both tiers have the equal instance, while minimize the cost, minimize the number of TSV.
Okay. Do you have other questions?
Yeah, so I noticed that your software is not rectangular. What did you use green plates underneath, or how did you ensure that cells belong to those non-rectangular software?
You mean how to ensure that the group instance within that submodules?
Yeah, because they are not square or rectangular, you have to do some kind of projection. I was wondering, is your projection GP or you use green plates like
after the IOP phase region planning, and then we determine the shape, and then we will use the legalization to try to force all the group instance inside that region, and so the region that we determine will try to preserve the distribution from global placement. Yeah.
Okay. Yeah. Thank you.
Yeah. We'll have a minute or two to have general questions at the end. I think we're going to try to get back on time because we're running a few minutes late. So let's thank the speaker again.